Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, I'm going to show you how to model a reservoir that will be converted into CO2 storage, and we will use MBAL software to do that. Okay, so it will be very interesting and very important because CO2 storage, CCUS, is a very important, and it will determine the future of oil and gas industry. And it is very good if we can model, if we can perform relatively simple reservoir modeling and simulation of CCUS using MBAL software. Okay, so we are now inside the MBAL software, and this is my model. The model is actually ready, so I'm going to show you what I have inside the model. So hopefully you can learn something from this, and you can also build your own case. Yeah, and because this model is already completed, hopefully maybe in the future I will also show you how to model, how to perform CCUS simulation starting from scratch. Okay. Okay, by the way, I will move this well first. Okay, first the introduction. So this is a hypothetical case, all right? Hypothetical reservoir, hypothetical wells, and this is my reservoir. It's actually a gas reservoir, previously gas producing reservoir. And of course, we want to convert this reservoir into a CO2 storage tank, yeah, CO2 storage. This is actually a condensate reservoir, okay, gas condensate reservoir. And you see we have aquifer, okay, and we will see whether this aquifer is strong or not. And Eng-Man, this is my gas producer, okay, gas producer. And before turning this reservoir into a CO2 storage, I will still continue production through this well. So there will be a step of production prediction in this video, in this exercise. And then I will convert this well to be a CO2 injector. And the future well is this one, CO2 injector, which is actually this well converted into a CO2 injector. Okay, so we will play with well scheduling later. Okay, so if you want to go from the start, click tool, and of course we will select material balance. Options, okay, reservoir fluid, general, okay, tank model, single tank, PVT model, simple PVT, production history. I will provide the production history by tank. And this is very important for CCUS. We must select fully compositional. Okay, tracking is not sufficient. And of course, black oil model cannot model CCUS. So we must select fully compositional. And you can also input the user information, company, field, for example, Eng-Man, location YouTube, and user comment CCUS. Okay, click done. And then from here, we go to PVT, fluid properties. All right, so this is the window for fully compositional PVT modeling inside the MBAL. Okay, so you must prepare the composition for your oil, composition for your gas, all right, and composition for your gas injection, and also the water. In this case, I provide water salinity, but you can also use table if you want. All right, start from oil, edit composition, and then you can provide the components, like in this case, nitrogen, CO2, hydrogen sulfide, methane, ethane, and then propane, isobutane, normal butane, isopentane, normal pentane, and then hexane and also heptane. Okay. And you can also include the heavier component like hypothetical components, C7 plus, C8 plus, and so on and so forth. Okay. And let's check. So by the way, you must include the mole percentage. All right. And then critical temperature, critical pressure, critical volume. you must insert the data here. Okay, so you cannot find the information, the values automatically provided by MBAL software. Okay, so you must prepare maybe from other spreadsheet or other software, or you prepare first the spreadsheet and then you copy and paste the table here. Okay, so eccentric factor, molecular weight, specific gravity, boiling point, and then volume shift, omega A, omega B, paracore, cost-out volume, cost-out AF, right? Viscosity model for oil and gas, you must select. In this case, I select default equations, Lorentz, Bray, Clark, for both oil and gas. Okay, and you see the molecular weight is 89.92. And then for stating or for determining the equation of state, you can go to change. And then in this case, I select Peng-Robinson. Correct CO2 density, yes. Fully compositional, yes. Reference temperature, 60 degrees Fahrenheit. You can also select hydrate model if you want to model the hydrate. Viscosity for oil and gas. Again, you select the equation. Blending, phase check, critical point. Okay, and I will use default settings for this. So I will select again Peng-Robinson as my equation of state. And also very important is here, phase envelope. It will be automatically generated. You can copy the numbers here and then paste on your spreadsheet and generate or plot your phase envelope. You can recalculate if you want. If you want, you can also generate the hydrate profile, but I don't want to calculate it. But you can easily click this button and then the data will be shown here. The result will be shown here. Plot. Okay, so this is our phase envelope for the oil phase. All right. Again, you can generate this kind of plot if you copy and paste information from this table, paste on your spreadsheet. Okay, so this is our phase envelope for the oil. Okay, you can also provide the properties here like formation GOR, formation condensate gas ratio, oil gravity or condensate gravity and gas gravity. All right. And yeah, the main important thing is pasting the data here, okay, the components. And you do the same thing with gas, edit composition. Okay, for the gas, of course, the main component is methane, 83% in this case. For equation of state, still Peng-Robinson, and the rest of the settings are the same with that of oil. You can also check the phase envelope, plot, and it is like this. Okay, click OK, click OK. Now gas injection is very important because we want to inject pure CO2. Edit composition. You see, the table should be the same. Okay, that's the requirement from MBAL. So the arrangement starting from nitrogen to C7 plus, it should be the same for oil, gas, and also injection gas. The difference can be in the percentage, of course. Like in this case, I will inject pure CO2. Okay, so the rest of the components will be very small. In this case, the default setting for very small or for zero is like this. And for CO2, of course, small percentage is 100%. Okay, so if you want to use MBAL for CO2 storage, you must use this setting. Okay, CO2, if you inject pure CO2, it will be 100%, and you maintain the format of the table like this. So you cannot paste only CO2 for one row cannot, MBAL will reject it. So you must copy the table, paste on this table, and then you change the percentage for the other components. And for CO2, it will be 100% if it is pure CO2 that you inject. Okay, and phase envelope, if you want to know, click plot. Yeah, because I use pure CO2, okay, so phase diagram will be aligned like this. Here we have supercritical. Below this curve, we have gas. Above this curve, we have solid and liquid. Okay. Close. Okay. Okay, so that will be the PVT section. And then we go to input, tank data. Okay. So the name of the reservoir is Eng-Man, Eng-Man reservoir. The temperature, assuming isothermal condition. Okay. Initial reservoir pressure, 2,210 psia, porosity 13%, connate water saturation 0.34, water compressibility, we use correlation, oil lag 0, okay, there is no oil lag initially in the reservoir, and the original gas in place, this value, okay, 30 something BCF, but of course you need to get good matching in order to be able to use this as your OGIP, original gas in place. And this is the start of production. Water influx. Okay, you need also to do matching to get the correct or the representative geometry of your aquifer. Okay, and by the way, we will skip the matching step for water influx for determining aquifer property because as you can see, the model is ready. So I'm just going to show you only the already populated data. Okay, and hopefully in the future we can also construct this kind of case starting from scratch. Rock compressibility, use correlation. Okay, but you can also use user specified if you already perform geomechanical laboratory experiment to know that the rock compressibility is actually changing with pressure, and it will influence the porosity and permeability over time. You can also input that, but in this case, I will use correlation. Rock compaction, like this, reversible, and then relative permeability. Okay, so if you have the relative permeability data, you input here. In this case, I will use Cori function to generate the curve, and then the endpoints are like this. The relative permeability for water, oil, and gas at the endpoint, and then the exponent is like this. Production history by tank. So I have the production history. I input into the tank. So as you can see, I provide history of the date, the pressure, cumulative oil produced or cumulative condensate produced, gas, and also water. Plot. Okay, so this is the plot for pressure. Okay, and then for the cumulative gas production. You can also plot cumulative oil production. Okay, cumulative gas production like this, cumulative water production. Okay, so I will close, click done. All right, so after inputting all the data, of course, we go to the next step, which is history matching, analytical method. Okay, so as you can see, I have achieved a very good match in this case. So I can use this gas in place to be used later in the simulation or in the CO2 injection forecasting step. Check regression. You see, I regress the gas in place and also the aquifer constant to get the good match. Okay, initial oil lag, I'm quite confident it's 0, so I will not use it for regression. Outer inner radius, I'm quite confident with 3. And then this one, time constant, also good. So I will regress only for the gas in place and the aquifer constant. Okay, so I'm quite satisfied with this quality of matching. Finish. We can also check the graphical method. Okay. You see for P over Z, it's quite good. All right. It's quite linear. So maybe from here you can say that the aquifer might not be very strong, right? Because we still have more or less a straight P over Z. P over Z over pressure, half Lena Ode, okay, like this. But they gave more or less the same gas in place. That's the good news. Okay, half Lena Ode for water drive. There is some deviation here, but that's okay. Coal, quite good, right? Roach, also quite good, except in this condition, but that's okay. Coal, no aquifer. And yeah. So overall, the graphical methods show that the gas in place is quite good. Also, the analytical matching also quite good. So we are quite confident with the gas in place when we want to model or when we want to forecast the CO2 injection, the gas in place can be used. And then energy plot. Okay, right, you can see. Actually, the water influx is not very strong, so you can see that the P over Z is quite linear. Porphyrium compressibility, also a minority. Okay, and of course, the fluid expansion is the majority or the dominant driving mechanism. Okay, next is WD function plot. All right, quite good as well. Run simulation if you want to show the all. Right, it's good for reporting if you want. Finish. Now it's also very important, run simulation. Hopefully the result is good. Click OK. All right. So this is the forecast or the simulation result for the pressure. Very good, right? So the model is relatively representative. So I'm quite confident to use this model as a modeling for CCUS or CO2 storage. Okay, so if we plot the simulation results, the tank pressure, and then oil recovery factor, gas recovery factor, average oil rate, average oil rate, average water rate, average gas rate, P over Z, and then aquifer influx, right? History, cumulative oil production, and simulation. cumulative oil production. Okay, so there is a discrepancy here. But that's okay, more or less the matching is very good. Cumulative gas production for history and cumulative gas production perfectly the same, right? For cumulative gas production between history and simulation. I will go back to tank pressure. Okay, I will close. Okay, so you see the matching, the simulation is very good, I think, yeah. So we can use the model to production forecasting, all right? And to get the good forecast, of course, I need to model the well. So let's go to the production well, double click. So you can see it's a condensate producer. The inflow performance, I use CNN method. Fractional flow, use tank. I provide the CNN values. Okay, the C representing the more or less reservoir productivity index, okay, or well productivity index. And then N is the exponent. So you can create the IPR. Okay, so the IPR is like this, assuming that the pressure can be maintained at this initial reservoir pressure. I can also calculate if I want to. And then more inflow, I will use the default setting. Outflow performance, which is very important for well constraints, no constraints, right? Well abandonment constraints, I will use default setting like this. Outflow performance will be based on this tubing performance curve, like this. Okay, so I import the tubing performance curve from Prosper. Okay, I import from Prosper, and the VLP or tubing performance curves are like this. I click plot like this. So this is the IPR and this is the VLP. Okay, you see they do not intersect each other. That's okay because we have option to extrapolate TPCs. So these TPCs, these VLPs, vertical lift performance or vertical lift performance curve will be extrapolated to intersect the IPR. Finish, click done, done. Okay, that's for the gas production well. And then let's check the CO2 injector. Well type gas injector, inflow performance like this. Okay, let's compare it with the production well. Okay, so you can see the CNN values are more or less the same. Here during production phase, it's 0.147 and of 0.86, whereas for the CO2 injection, I can maintain the C 0.147 and N 0.18 something. I can maintain that. So let's maintain, assuming that when the well is converted from gas production well to CO2 injection well, there will be no change in C and N, okay? Because I do not interfere with the perforation. So I can paste the value here because it's actually the same well. I just convert from gas production well to CO2 injection well. So I can maintain the CNN value. Like this, and I can generate the plot. So you see, this is the IPR for injection well. It is, of course, different with IPR of producer or gas production well. In production well, the IPR will be like this. it is curve, right? Starting from the left to the right, okay? But in injection well, it is like this, okay? Like this, right? So this is the IPR during production phase. This is the IPR during the CO2 injection phase. Okay. And then calculate if you want. More inflow. The setting is like this. Outflow performance, no constraints. And for tubing performance curve, I also import from Prosper. So I've prepared the CO2 injection well modeling in Prosper and then import here, import, so that I get this one. If you plot, it is like this. It's quite weird, but yeah, maybe we are familiar with VLP of production well. It is an injection well and it is CO2. So that's okay if the VLPs or if the TPCs are quite weird looking. Okay. But it is very important that you generate the VLP, the tubing performance curve from, for example, Prosper, and import the result here. Click done. Okay, so we have discussed the well modeling for production well and also for the injection well. Now let's go to the production prediction setup. Now we tick this oil leg production, gasket production, okay, common manifold for oil leg and gasket producer, okay, and gas injection, we tick that also because we are performing CO2 injection operation, and we allow water production. Use fractional flow model, and for the predict, of course, we select production profile using well models. Prediction start from this date, prediction end at this date. Click done. Let's go to production constraints. So the constraints are quite long. It's the setting, the setup, the constraints during the production phase. And later I will put some constraints for the next production. Okay. So I'm going to show you first, and then I will do the modification later. And here, the constraint for the injection period, I start from 2025. I set the gas injection manifold pressure to be 1,500. And I put the maximum gas injection rate of 17 mmscf per day. Okay, 17 mmscf per day. And this is the injection manifold pressure. So click done. Well type definition already discussed for CO2 injector and production well. Eng-1. Click done, and then well schedule. This is very, very important. Okay, so this one, I will add new well. Actually, I just convert the well, and this CO2 injector, well type definition CO2 injector, one well, no downtime. I start this well in January 1st, 2025. So the setting is like this. And to allow the production forecasting to continue at least until 2025 January, I will enable this row. So starting from this date to this date, I will allow one well, which is Eng-1, to continue to produce. Downtime also 0. Click done. Reporting schedule 1 month. Run prediction. Calculate. Let's see what happened. Okay. So we plot. Okay, so this is the result from gas reservoir. The blue line is simulation tank pressure, and the green line is actually history tank pressure. Again, they are matched. And this is the prediction tank pressure. The tank pressure continue to decline. Okay. And this is the gas injection rate, the black color. You see, we can achieve 17 mmscf per day until December 2030. And after that, the injection rate continues to decline. At the same time, because we inject CO2, the reservoir pressure continues to increase like this. Okay. By the way, I can also show you the gas rate. Okay. And then gas injection rate like this. This is the prediction. I can also show you the simulation coming from the history like this. So no production in the early phase. And then this is the production history calculated by the simulation. Okay, and then starting from here, we continue to produce. This is the predicted gas rate. And then we end the gas production step in the end of 2024, and starting from January 1st, 2025, we convert the well and we start injecting CO2 at 17 mmscf per day, and after that it declines. Very interesting, right? So this one, we can also plot the CO2 profile during prediction like this. This is CO2 profile, CO2 percentage in the reservoir. So it increases, right, as the injection progresses. We can also plot gas saturation. Okay. We can plot simulation, aquifer influx, and prediction. Where is the aquifer influx? Like this one. So the aquifer influx will decrease as the reservoir pressure increases due to the injection of CO2, right? So if I also show the simulation tank pressure like this, so reservoir pressure decreases, water influx will increase, okay, to balance the reservoir pressure decline. But after we inject CO2, the reservoir pressure will increase, and at the same time, aquifer influx will decrease. So you can learn many things in this exercise. I will minimize, okay? And then we can click done, and then we go to well results. You can plot the well results from Eng-1, the production well. Let's say I want to plot flowing bottom hole pressure and then the gas rate. Okay, at the end of the production phase, the rate will be decreased to 0. And then if you check the CO2, okay, it's 0.84% for the Eng-1. You can check again the PVT, the gas, 1.84. All right, so if you check the Well results plot, it is 1.84%. It's constant. We can also check the gas rate again, and then what else? CGR, water gas ratio. Okay, but one of the most important things, of course, CO2 injector. You can plot the tank pressure, flowing bottom hole pressure. And as you can see, we start with flowing bottom hole pressure or injection pressure greater than the reservoir pressure. But along with time, as the injection continues, the reservoir pressure increases. Okay, reservoir pressure increases. So we need to provide higher bottom hole flowing pressure to maintain the 17 mmscf per day target, right? But at one point, the pressure is equal. And if we continue to inject, the well cannot inject any longer because the reservoir pressure is already very high. So it will decrease the injectivity significantly. If you want to check the CO2, you see for CO2 injector, as per PVT input, the CO2 percentage is 100, right? So I can also plot again tank pressure and then flowing bottom hole pressure, manifold pressure or wellhead pressure. So you can see this is the wellhead pressure, and we can also plot the gas injection rate. We can maintain 17 mmscf per day, but then it declines as the difference between the reservoir pressure and the flowing bottom hole injection pressure continues to be smaller and smaller. And if you want to know cumulative gas injection, it's like this. It is in million standard meter cube. So we need to get density value to convert this volume unit into a mass unit, right? Because at the end of the day, I want to know how many tons of CO2 I can inject, I can store in this reservoir. Okay, so yeah, that's almost all of the things that I can and I want to show you. So we have prepared the reservoir, we have prepared the PVT, the compositional PVT, we provide all the data important for history matching, and then we achieve good matching with analytical method, with graphical method, with numerical method or simulation. And after observing that the matchings are very good, we go to production prediction phase. First, we continue production until the end of 2024. Okay, we use this well model, and from the beginning, from the start of 2025, we convert the reservoir into CO2 storage, and we convert the well to be CO2 injection well. We provide the TPC, we provide the injectivity, and then we continue with CO2 injection prediction step. Okay, we get the gas injection profile, we get the reservoir pressure profile, flowing bottom hole pressure profile, wellhead pressure profile, and then we can get the cumulative gas injected, which later on we can convert to mass of CO2 injected in the storage. So we will use tank model to simulate our CO2 storage or CO2 injection. Okay, so previously we have learned about the characteristics, something that we have in this model, in this simulation. And let's say now in this video, I will show you if I have another scenario regarding the production constraints, if I already have specific target regarding the production, and also regarding the timeline of the project, how can I put that strategy inside this MBAL software? Okay, so I'm going to show you. Okay, so here in this table, we have the production constraints or strategy or control, something like that. Okay. This strategy, for example, manifold pressure or wellhead pressure, and also the maximum water rate already been populated, already been set up. But I want to add constraints. I want to add control for the production in the future. And as you can see, for the future control, I have two rows. This one in 2023, where I put my manifold pressure to be 164 and maximum water rate to be 4 stock tank barrel per day. And also for the CO2 storage, CO2 injection, I put future control for 2025, where I set that the maximum injection gas rate that will be allowed is 17 mmscf per day with maximum manifold pressure or wellhead pressure of 1,500. Now I want to put another strategy, another control, another constraints. So I will first deactivate these two rows. Okay, I don't need to erase them. I do not need to delete them. I just make them inactive to preserve them. Okay, and then I will put some constraints. Let's say at February 2022, I want to allow maximum gas rate. Yes, maximum gas rate to be 3.155. And then I will do that until 2024. And then this one, 4. You can follow me, or you can also fast forward until I reach 2024. Now it's July and August. I know it's quite tedious, but I think I prefer doing this than copy and paste the entire table. Okay, I can also do that, like I will clear table and then copy and paste the strategy here. But in this case, I will rather input manually to show you how to do it. Okay, it's December 2022. Now we go to 2023. Okay. I think it's more efficient. January, February, then this one, March, April, May, June, July, August, September, October, November, and lastly, December. And you see the January 1st, 2023, the original constraints will be there, automatically, okay, arranged. Now we go to 2024. Oh, sorry. It should be like this. And then this one. June, July, August, September, October, November. Okay. Okay, and then November, and then December. Okay, and then for 2025, January, February, March, April, May, I will allow the production to continue to March. Okay, so this one should be okay. Sorry. Go to 2024. Oh, sorry. Change it to February 2025. And this one to be March 2025. Okay. Now I have my production strategy. Let's do the setup. In March 2022, my production target, let's say, okay, and then for the April, and then for the May, okay, I think I will pause the recording and see you until I complete all the production strategy. Okay, so I've completed the production setup. So you see, this is the, let's say, production target from 2022, 2023, 2024 till March 2025. And then I want to, let's say at April 2025, I want to shut in the field to prepare it to be converted to CO2 storage. Maybe I will need some pipeline installation and others. So I will stop the production in April 2025. Okay. And then I will inject the CO2, let's say in January 2026. So previously, this is my control for injection. I will change it to 2026. The target still 17 mmSCF per day, but let's say I don't want to constrain the wellhead pressure. So I will delete it. And never mind these two rows, it's just typo. I don't want to delete it. Okay. So yeah, automatically the CO2 injection control moves to the bottom in January 1st, 2026. So it's like this, and you can also plot. Okay, this is currently we are showing the manifold pressure. Change the variables. I want to plot the gas rate. Okay, so it's like this. Okay, so finish, done. And to make sure that I will shut down the injector, or I will shut down the producer at April 2025, I will go to well schedule and I will change it to April 2025, okay, or March 2025, so that at April, it will be, the production will stop. And then this one, I will change it to 2026. So click done. And let's say what happens. Calculate. The gas injector manifold pressure has not been entered correctly over all the times that the gas injector wells are active as defined in the drilling schedule. Okay, so as you can see here, we need to provide manifold pressure. Okay, the gas injector manifold pressure. Please go to the production prediction, production and constraints to correct the problem. Okay, previously I put 1,500. Let's say I want to allow higher pressure. let's say 1700, to ensure that along the wellbore, across the wellbore, I will maintain the CO2 in the dense phase or in supercritical condition. So click done, run prediction, calculate. Let's see what happened. The important thing is I want to make the production in 2022 to the end of production, which is March 2025, as per my target. So click OK. So it's like this. Okay, let's see, starting from none, simulation, I want to plot gas rate. Okay, so this is the average gas rate calculated by the simulation, and then the prediction gas rate. Okay, so it's like this. Something wrong here. Okay, let's check, by the way, to 2022. Okay. Okay, this one. This is the gas rate, or if I go to the well results, 2022, the gas rate is this, and then March. So the model cannot reaches the target because the target is the maximum gas rate. Okay, the model cannot give that high. For example, this one in February 2022, I set the production prediction to be 3.155 mmscf per day, but in this case, I only get 2.57, or here, this one. Yeah. So it means that the current model cannot give that high rate. It's okay, by the way. And here, end date is March 2025. So I should correct. Well, schedule should be to April, because I want to stop the production at April. In March, I still have production. I will recalculate. Okay, plot. Okay, so it's like this. What happened here? April 2023, let me check. What happened in April 2023? Oh, in April 2023, it should be 2.098. Click done, rerun. Okay, plot, it's so good. Let's check if I can still produce at March 2025. This, I can still produce, yeah, I can still produce at 0.796, which is the same with my target. So it's good. I will, by the way, if I check the reporting schedule, okay, I will check. It's 30 December 2020. User defined. By the way, I want to make it the same. Prediction start. Okay, let's see. Let's say this one, December 1st. So that each time step will start from day one, date of one. Okay. I think it's more comfortable for me to check. So 2022. Yeah, my expectation is 3 mmscf per day, but the model cannot give that. March also cannot be higher than that, but that's okay. Okay, and then we continue with gas injection rate. By the way, this one, simulation and average gas rate, prediction gas rate, and then gas injection rate. Okay, it's like this. I shut the well in for several months to prepare it to be converted to injector. And then I can inject at 17 mmscf per day. And I can also check the well results. CO2 injector plot. I want to see gas injection rate. Okay, and then tank pressure. Tank pressure keeps increasing. Flowing bottom hole pressure. Okay, manifold pressure. And you see the maximum manifold pressure that I allow is 1,700 psia. Okay. By the way, I can also calculate the allowable reservoir pressure, final reservoir pressure at the end of the injection period. For example, like this. The reservoir pressure is, initial reservoir pressure is 2,210. And I can inject, I can continue injection. I can increase the reservoir pressure to achieve the initial reservoir pressure, which is 2,210. Okay, so I can continue my CO2 injection. I will store my CO2 until the reservoir pressure reaches initial pressure, which is 2,210. But I can inject more actually. I can inject more, I can increase the reservoir pressure more, but I cannot exceed the fracture pressure. Okay, so it's very, very dangerous. I cannot exceed fracture pressure. And let's say the depth of the formation is 4,500 in feet. And if the fracture gradient is 0.7, so the frac pressure is 3,150. 3,150. So I can continue my injection. I can store my CO2 continuously until the final reservoir pressure is relatively close to 3,150, which is the frac pressure, but still well below that. Let's say I will make the maximum final reservoir pressure to be 2,700. Okay, 2,700. And if you check the result, if we check the reservoir pressure, it's still oh, it's already 2,800. Okay, I don't want to exceed 2,700 actually. So let's say I want to reduce the maximum wellhead pressure to be, let's say this one. Okay, or 1,650. so that I will not exceed 2,700 as my final reservoir pressure. So this kind of exercise you can do using MBAL, and it is of course relatively simpler than 3D model, okay, than 3D reservoir model. But of course, MBAL model has its limitations. Okay, so I recommend you to construct the MBAL model, but also prepare your 3D model. Click OK. Let's check the final reservoir pressure. It's 2,768. Exit a little bit, so I will reduce, let's say, to 1,600. Okay. What is the final reservoir pressure? 2,730. Okay, you understand what I mean? So I will continue my injection until the final reservoir pressure is 2,700. And I want to plot the average gas rate and average gas injection rate from the prediction. Okay. Okay, so this is the final result. And also, sorry, gas rate. Yeah. So this is the final result. This is the reservoir pressure. And then the reservoir pressure continues to decline because we continue production till March 2025. And then we shut in, and then we continue with CO2 storage, the gas injection rate of 17 mmscf per day. The reservoir pressure continues to increase. Okay. Yeah. And then because the difference between reservoir pressure and flowing bottom hole injection pressure continues to decrease, of course, the injectivity will drop and the injection rate will decrease. Okay, so I think that's all. I hope you got important things from here, changing the scenario, changing the strategy, changing the control, and then plotting the results. Okay, so thank you so much and see you again in the next MBAL and CCUS video. Thank you.